When we're talking about conservation of momentum, one easy way to do so is to use momentum bar charts. In the same way that we use energy bar charts in order to show that energy can be conserved inside of a system, we can do the same thing with our momentum. Now, there are 4 steps that I recommend we follow when we're going to be solving conservation of momentum problems using momentum bar charts. The very first step is to specify the impulsive force event that separates the initial and final situations. So for example 1, cart A with a mass of 0.5 kilograms and cart B with a mass of 0.5 kilograms are both at rest. That's why I've represented over here on the left. The plunger is extended and both carts move in opposite directions at a rate of 0.1 meters per second, represented over here on the right. Construct a momentum bar graph to represent the situation. Well, the very first step to solving this is to specify the impulsive force event that separates that initial and final situations. What's happening here is the plunger gets extended. That is going to be our event. The plunger is extended. If we want to actually relate that to a specific force, that is going to be the force normal on cart B by cart A and force normal on cart A by cart B. If we're talking about the specific impulse force that we're going to have there, it is both of these. Equal magnitude, opposite in direction. The second step, designate objects in the system by listing the object, its mass, and its velocity in the chart. Use variables for any unknown quantities. Well, for my initial situation, which I have set up on the left-hand side, we have cart A. And we are told that for cart A, it has a mass of 0.5 kilograms, and it is at rest. So it has a velocity of 0. Now these masses are all going to be in kilograms, and these velocities should all be in meters per second. We're also told that the initial situation we have cart B. Cart B also has a mass of 0.5 and a velocity of 0. For the final situations, we still have cart A and we still have cart B, and neither of their masses have changed. So I'm still writing both of those down, and I'm still showing that we have the same mass. But now we have a different velocity. Instead of neither moving, they are both moving at that rate of 0.1. However, they're going in opposite directions. Because I'm showing cart A traveling to the left and cart B traveling to the right, I'm going to use that to set up my signs. So for cart A, because it is traveling to the left, I'm going to say that that is a negative velocity. And cart B is traveling to the right, so I'm saying that is a positive velocity. Velocity is the speed and the direction of travel, and that's what we're going to be representing with step 3 now that we have finished identifying our objects, their masses, and their velocities. Step 3 is to draw a horizontal bar to represent the size and direction of the momentum for each object. Well, one thing that we should keep in mind is that momentum, represented with a lowercase p, is the mass of an object times its velocity. So for cart A, in the initial situation, it has a mass of 0.5 and it has a velocity of 0. So we're not going to have any momentum. So instead of drawing a bar, I'm just going to indicate that on the 0 line. There's 0 momentum for cart A. Actually, it's going to be the same thing with cart B. There's not going to be any momentum for either of those two carts. Now, for our final situation, cart A still has its mass, and it is now traveling in the negative direction, so negative 0.1 meters per second. So it is going to have a momentum. So I'm going to represent that, let's say, with 2 bars. There are 2 bars going in the negative direction that we have here. So because this thing is traveling in our negative direction, that's why we have negative momentum. Cart B is traveling in the positive direction, so positive momentum. It is traveling just as fast and has just as much mass, so I'm going to show it too has those 2 bars of momentum. Overall, I'm starting off with 0 bars of momentum. At the end, I have negative 2 bars and positive 2, which when we add those together will also equal 0. So I am showing that my momentum is going to be conserved. The fourth step, now that we have set up our bars on our charts, is to write the conservation of momentum equation for the bars and solve for the unknown quantity. Well, what we are really seeing here is that all of our momentums initially, when we add all of those up, are going to be equal to all of our momentums at the end that get added together. So the sum of our momentums at the beginning are equal to the sum of all of our momentums at the end. If we're actually going to be writing that out in terms of individual momentums, what that is going to be is it's the momentum of cart A at the beginning plus the momentum of cart B at the beginning for the initial situation is equal to the momentum of cart A at the end, the final, plus the momentum of cart B at the end, or the final. And then if we wanted to go even further, solving for like a mass or a velocity, if we didn't know any of those, we'd just be showing that is going to be the case. Mass A times velocity A plus mass B times velocity B is equal to mass A times velocity A plus mass B times velocity B. That's how we can set up our conservation momentum equation for example 1. But we don't need to use this to solve for any unknown variables because we know all of those unknown variables.